Good morning, Townview. So today we're going to be talking about atomic structure. So at the top of your journals, let's go ahead and write that down. Atomic structure. Let's go. All right. Can anyone tell me what I mean when I say atomic? Just say it. All right. So it's related to the atom. What about when I say structure? All right. How it's built. Good. That's basically what we're going to be talking about today. How it's anymore. At that point, you have an atom. All right, so prior to atomic theory, the Greeks believed that all matter was made up of four basic elements: fire, earth, water, and air. Please do not write this down. I'm just telling you all this. So prior to atomic theory, this was the common belief. And this is my boy Democritus. Democritus was a Greek philosopher. There's not much you need to that can't be broken apart anymore. He came up with the idea of the atom. The word he came up with was atmos, or atomos. All right, next up we have John Dalton. Not much to write on this page. So first I want y'all to write his name. So John Dalton. Who is John Dalton? He's the father of the modern atomic theory. So this guy is the father of the atomic theory. On the next page, we're going to write down the things that he said. You don't have to worry about writing down any of this. Father of the atomic theory. So the modern atomic theory. Go over them one at a time. So the first one is that all matter is made up of tiny, indivisible particles called atoms. So not every one of Dalton's postulates is considered to be true today. However, you do need to know every single one of these postulates. The reason being is on my exams, the way these questions are going to look is you're going to see 4 of these answer choices. One of them is going to be true and the others will be false. Or you'll have 3 true and 1 false, and you'll have to identify which one is not one of Dalton's postulates. So you do have to have an understanding of what these are saying. Let's look at the next one. The next one says that all atoms of a specific element are identical. So if you want to write the whole thing, you can. But when I say identical, we're assuming identical in mass, size, and properties. So all atoms of a specific element are identical. Basically what he's saying here is oxygen in Japan is the same as oxygen in China, which is the same as oxygen here in the US. He's saying that they all have the same size, they all have the same mass, and they So as we move to the right and down on the periodic table, elements are getting larger. So they are different in size and they do exhibit different properties. So this one is still true. Atoms of different elements can combine with each other. Atoms of different elements can combine with each other in fixed whole number ratios. This one is very important. So can anyone tell me the formula for water? All right, good. So H2O is the formula for water. Is HO.5 a thing? Why not? Can we have half an oxygen atom? No, we can't. So basically he's saying that we can't have fractions. They're all going to be whole number ratios. The last one is atoms can be rearranged, they can be combined, they can be separated in chemical reactions, but they cannot be created or destroyed. We'll talk more about that on the next slide, but this is law of conservation of mass. So I'll give you guys a second to write this down, and then we'll talk about it some more. All right, so let's go ahead and discuss. All right, so let's go ahead and talk about these some more. So all matter is made up of tiny indivisible particles. What part of this is untrue? Can anyone tell me? All right, go ahead.
Is it the part where it says they're indivisible?
All right, indivisible is correct. So what we've learned since Dalton, so Dalton was 1800. What we've learned since then is if you were to take a particle, and the particle that they work with is typically hydrogen. So let's look at the periodic table. So hydrogen is the smallest element on the periodic table. It's made of only a single proton. So if you take a proton and you make it spin very, very fast, you take another proton, make it spin very, very fast, and then you make them collide, you can recreate the Big Bang. And when you do that, you break the protons. When you break the protons, they form these things called quarks. So basically, we know that an atom is not the smallest thing. There are things that are smaller than atoms. You can break an atom. So this is no longer considered true. However, it is Dalton's postulate, and you need to know it. The next one is all atoms of a specific element are identical in mass, size, and properties. So in parentheses, I want you guys to write isotope. All right, so what is an isotope? An isotope is the same element with a different mass. The example that I like to go with is carbon. So we are carbon-based life, which means we are made of carbon. And everything alive on Earth is made of carbon. So trees are carbon, bugs are carbon, everything is made of carbon. So we are all made of carbon-12. We also have a little bit of carbon-13 and very, very little carbon-14. So carbon-14 is radioactive. All three of these are carbon, but they're all different from each other. They each have a different mass, and they each have different properties, which means this statement is incorrect. So all atoms of a specific element are identical. We know that's not true because we know that isotopes exist. We'll talk more about isotopes next class, but I just wanted y'all to know that that's an untrue statement because of isotopes. All right, now the rest of these are still considered to be true. It's just those first two that have been heavily disproven. Let's go ahead and keep moving. All right, next up we have the law of conservation of mass, law of conservation of energy. We'll be talking about this one all year, so let's go ahead and write it down. So law of conservation of mass states that mass can never be created or destroyed in any process. So basically over on this side we have 4 oxygen molecules. Over here we have 8 hydrogen molecules. And then here we produce 4 water molecules. It basically means whatever we have on the right side needs to exist on the left side. Nothing can be destroyed or created on either side. And we'll be doing this all year long. Not everybody knows. All right, let's keep moving. All right, so next up we got my boy J.J. Thomson. All right, so here's what you're going to write. J.J. Thomson. I don't think I've ever seen Joseph show up on any test or quiz, especially mine, so I don't use his first name. You just need to know him as J.J. Thomson. Next, you need to know his experiment. His experiment is the cathode ray tube. So I want you to go ahead and draw the cathode ray tube, this thing right here. It doesn't need to look perfect, but just know you're going to see this again. You're going to see it on my quiz, you're going to see it on my test, you're going to see it on the ACP, and when you see it, you need to associate it with my boy JJ. Actually, so cathode ray tube is just what's inside old TVs. All right, so let's go ahead and explain the cathode ray tube. So basically, so y'all know how electricity works. You have a wire, and you have a positive side, and you have a negative side, and then electrons are just going to flow from the negative side over to the positive side. So electrons are just going to flow from one side to the other. That's how electricity works. Now, in a cathode ray tube, what you have here is a vacuum tube, which means all the air was taken out of the tube. And then here we have our anode, and here we have our cathode. And what we're going to do is apply the electrical current into the cathode ray tube. So basically, it's the same as a wire, except there's no wire. The electricity just flows through the tube itself. Now, the electricity is flowing through this tube. So what J.J. Thomson did was he applied a positive charge over on this side, outside of the tube, and then a negative charge on the bottom. What he noticed, and I know this thing keeps moving, but it shouldn't move. What he noticed was the cathode ray tube, or the particle that was running through it, was attracted to the positive side. If it's attracted to the positive side, what kind of charge does the cathode ray tube, does the particle in the cathode ray tube have? It's got a negative charge. So what J.J. Thomson did was he discovered the first subatomic particle. What does subatomic mean? All right, smaller than atomic, and the things that are smaller than atomic are protons, neutrons, and electrons. He discovered the first subatomic particle, which was the electron. So J.J. Thomson, cathode ray tube. You should have drawn the cathode ray tube, and then write that he discovered the electron. We'll talk about the electron's mass later, but as long as you wrote what I told you, you'll be good. Do we all have our picture? We all drew the cathode ray tube? Interesting fact, YouTube was named after the cathode ray tube. Anybody heard of a CRT TV? Nobody? You have? So it's the old TVs, just the big bulky TVs. Those have cathode ray tubes in them. They're called CRT TVs. And people back in the day, like in the 70s and 80s, they called the TV the tube. So YouTube was, you get to make your own TV, whatever. You know, that's the idea. I know. Those of you on camera, y'all didn't hear that. She was like, oh. I'll cut that out in editing. All right, let's keep moving. All right, so the last thing you're going to write from our boy J.J. Thomson is the plum pudding model. Has anyone ever heard of plum pudding? You have, really? Don't lie.
I've heard of the food.
Okay. So I always thought it was a pudding, sort of like apple pudding, or not apple pudding, like pudding. Y'all know pudding, the ones that come in little things and kids eat them. So plum pudding is actually a European dish, and it's this thing right here. It looks pretty gross. But I would like to try it. So if anybody here wants to make us a plum pudding, I'd be happy to try your plum pudding. No, it's supposed to look like that. You like eat it with tea or something, right?
With tea?
Probably. It's like those tea drinking countries.
Wait, where is it from?
It's like a UK dish. Here, hold up. I don't wanna speak things that I don't know about. All right. Shh. So plum pudding originated in the UK. That's one of the tea drinking countries that we were talking about. See, and the picture that I chose is much better looking than the rest of these. If your plum pudding looks like this, I'm not touching it.
That looks like chocolate. Is that chocolate?
But it's not though. Like, if somebody handed you this and told you it's not chocolate, would you eat it?
No. Wait, why is it
All right, somebody make. This one looks gross. Somebody make us some plum pudding, and check this out. So they pull up the plum pudding model. Anyway, shh. Let's get back on task, please. So, why did he call it the plum pudding model? So, we knew about atoms, but we didn't know what they looked like. So they had to come up with an idea or a theory of what they thought an atom actually looked like. So his thought was the mass was evenly distributed throughout the atom, which basically means all of the mass of the atom is spread out evenly throughout the atom itself. Now, they're going to be all side by side. and we'll discuss more. But basically, his thought is the cake is the positive charge, and then the blueberries. So I bring a blueberry here just because we all know what blueberry muffins look like. So the cake is the positive charge, and then the blueberries are going to be the negative charge. So that was the idea of the plum pudding model. But the thought was atoms are like the mass is just evenly distributed throughout them. Let's keep going. Next up, we got my boy Ernest Rutherford. Go ahead and write his name. And he came up with the gold foil experiment. All right, so here's what Ernest Rutherford did. So Ernest Rutherford, he got this photolithic paper. Who here's seen a Polaroid? Most of y'all seen them. So what happens if you take the film out of a Polaroid? What happens to the film? All right, so it processes it. It just takes the light and then it absorbs it, and then typically it'll just turn black. You'll ruin the film. So this is some photolithic paper, and this photolithic paper, it glows when it's hit with an atom. So over here in the center, you have this gold foil. And the reason he used gold is, let's all take a look at gold. So gold is right here at the bottom of the periodic table. It's one of the heaviest elements on the periodic table. Very heavy and very large. So it acts as a good element to use for this particular project. And then he took a lead box. So here's his lead box. Anybody want to guess why he used lead? Anybody know some properties of lead besides poisoning children? What is lead good at? All right, so it's not in pencils, that's graphite. So it's a metal, so it's not an insulator. Say it again?
It lets light through.
Lets light through. It's a metal. It's a conductor, yes. Anyway, so who's been to the dentist and had lead put on them? Why do they put a lead jacket on you?
Because it doesn't let the radiation through.
All right, because it blocks radiation. It's really good at blocking radiation. So he took this lead box. He took this lead box, and then he put some radioactive material in it. Now, radioactive material is giving off radiation in all directions. But once he put it in a lead box, the radiation was kept inside the box. But then he took a rifle barrel and he installed it on the box. So what did he just make? He made a ray gun, and he was shooting alpha particles at people. Not at people, though. Not at, So he built this ray gun, and then he started shooting it at the gold foil. Now, what he was trying to do was he wanted to disprove the plum pudding model. He didn't believe that the mass was evenly distributed. But if the mass was evenly distributed, one of two things should happen. I want everyone to pay attention here. So if the plum pudding model was correct, one of two things should happen. Either all of these particles that he was shooting, either all of them go straight through, or all of them should be blocked. So that's what should have happened if the plum pudding model was correct. But here's what he ended up finding. 80% were going straight through, and then 20% were bouncing off and then just hitting random parts of the photolithic paper. So why is that?
Because they all have different structures.
What do you mean?
Like they're all built different.
So he's shooting alpha particles, which are basically helium atoms, and the gold is just gold. So helium is being shot at gold. So why are some of them bouncing off and then some of them going straight through? All right, so here's what he discovered. He discovered that the plum pudding model is incorrect, and that all of the mass is in the center of the atom. And that's not what I wanted to draw. So all of the mass is in the center of the atom, and the atom is just surrounded by a bunch of empty space. So here we have another one, and it's just surrounded by empty space. So when you shoot these particles, what happens is a majority of them are just passing through the empty space. And all the ones that pass through the empty space, that's the 80%, are just going straight through. But what about the ones that are going really close to the nucleus? What happens to them? They either bounce off, get deflected, or they're repelled by the positive charge. So one of those two things is happening. So either the positive charge is repelling them, or they're bouncing off and then hitting the walls. But that's 20%. So 20% are doing this, and then 80% are just going through the empty space. So this right here is called the Rutherford model. And in the Rutherford model, here's what I want y'all to write. Rutherford, he discovered a positively charged nucleus, and he discovered that most of the atom is empty space. So he discovered the positively charged nucleus, and he discovered that a majority of the atom is made up of empty space. He also gave us this really cool looking model of the atom. I'll draw a better one. Here, I'll do it for y'all now. It's basically the SEM logo. All right, let's keep moving. Next up, we got my boy Chadwick. So Chadwick, he worked with Rutherford. You don't got to write much about Chadwick. He's actually not tested. But I do want to talk about him because he did something important. So Chadwick, he discovered the neutron. So how did he do this? At the time, they knew about protons because of Rutherford. They knew about protons. So something like boron would have 5 protons, but it would have a mass of 10 or 11. Nitrogen would have 7 protons, but it would have a mass of 14. Basically, there was a bunch of mass that they couldn't account to being the positively charged protons. So he thought that there was something there that they couldn't identify. And in his experiment, he did something very similar to Rutherford, and he discovered the neutron. So the neutral atom that was very difficult to discover, but it was there. All right, let's move on. Last up, we got my boy Bohr. Who remembers the Bohr model from middle school? All right, good. So we don't teach Bohr model anymore because y'all learned it in middle school. We might later, but not now. All right, so first we're going to write Bohr. All right, so Bohr gave us the electron cloud. He expanded on Rutherford's model. He told him, yeah, I like the idea of the nucleus. And he believed that electrons, they spun around the nucleus in orbitals the same way that planets revolve around the sun. So he thought that they had a fixed route that they took. So these 2 electrons are going to stay on this fixed route, and all they're going to do is spin in this route. One is going to spin this way, the other one's going to spin that way, and that was his idea. Now, who's heard of Heisenberg? All right, not Walter. Who's heard of Heisenberg? All right, so Heisenberg, he gave us the uncertainty principle. What he says is you can't possibly know the speed and direction that something is moving, and also the location, which basically means you can't know that something is in this particular spot in this particular orbital. So he came up with this model right here. Everybody take a look. So this is Heisenberg's model. And in Heisenberg's model, the darker the blue, the more likely the electron is going to be there. So this is the current best model of what an atom actually looks like. It's not actually Rutherford's model. It's this model right here. So this is the best model because it gives us probabilities. It tells us that it's very likely that you're going to get an electron here. It's very likely that you're going to get an electron here. Very likely you'll get one here. It's very unlikely that you're going to get one here because there's no dot there. But that's basically what this model is telling us, and we got this one from Heisenberg. Any questions? Or y'all got this? All right, let's move on. All right, so next up we got the structure of the atom. This is going to be really short. So the nucleus, let's go ahead and write this down. This is the dense central part of the atom, and it's where the protons and the neutrons live. So protons and neutrons both stay in the nucleus. They never exit the nucleus. Then we have the electron cloud. That's the large area outside of the nucleus, and this is where the electrons stay. Go ahead and write this down. I'm going to give you all a lap. All right, so let's keep on moving. Shh. We're almost done. All right, so real quick, I want you guys to draw this in your journal. I want it to show all the same categories as this one, and then we're just going to add a little bit more to it once you're done. I'm going to give you guys a couple of minutes, and then we'll talk about it. All right, so protons, where do they stay at? And their charge, where you put charge, I want you to put +1, and you'll see why in a minute. Now, when we talk about relative size, it says large. That's compared to a electron. I want you to write 1 AMU. Who remembers AMUs? Who remembers AMUs? For real? Atomic mass units. 8th grade. Come on, guys. All right. Shh. Next up, we got neutrons. Where do they stay? And what's their charge? All right, now their size is also going to be 1 AMU. For our chemistry, for all intensive purposes, a neutron and a proton have the exact same mass. They're both 1 AMU. All right, electrons, where do they stay at? And then for charge, we're going to put -1. So 1 electron will counterbalance 1 proton. So 1 proton and 1 electron will create a net charge of 0.
Is that why they can't both be
We'll talk about that later. We're not there yet. All right, so relative size for electron, we put tiny. It's 1/1840. So it's very, very small compared to, and this is AMU. It's very small compared to the proton. And for as far as you guys need to know, they have no mass. So they do have a very, very, very tiny mass. However, in our chemistry, don't assume that this number, everybody look at my periodic table, don't assume that the 108 back here is the mass of the electrons. That's not what that is, okay? This 67 back here is not the mass of the electrons. So as far as you guys know, electrons have no mass in my chemistry class. Anyone need more time here? All right, let's move on.